So think back to when we learned about functions. Uh, how do we tell if a graph is a function? Vertical line test. So the vertical line test says if you draw a vertical line, the given graph is only a function if the line hits less than twice. So one time or fewer. So if you look at that, every one of those is only hit once. If I were to graph, say, a circle, then that is not a function because the vertical line hits twice. What rule is it breaking? Well, it doesn't pass the vertical line test, but why is that a problem? Why is that not a function? X cannot equal 2y's, which I think is what you were saying. So if we go look at the bubble form of functions, I'm going to do 3 different ones. So if I have this, is that okay? 2 different x's hitting the same y. Yeah, that's fine. And then if I had this, that would be a function. But if you have one x that hits 2 y's, then it ceases to be a function. So more specifically on the graph, so that's -4, so -4, comma 3, and then -4, comma -4. So that's like saying -4 is hitting 3 and -4, and that breaks the rule. I like to use the idea that one person cannot be in 2 cities at once. Not completely within 2 cities at once. You can have more than one person in the same city. Now we need to review a little bit about inverses. So, oh, that's not what I wanted. So let's look at a particular function, x squared. Is x squared invertible? What does it mean to be an inverse? Flip it opposite what? Well, there are multiple types of inverses. We could have additive inverse. So if you took a function and you changed all of its signs, positives to negatives, negatives to positives, that would be the additive inverse. And that would flip across the x-axis. Well, it depends on where you put the negative. It could be x or it could be y, depending on if you put it inside or outside the function. Okay? You could have the multiplicative inverse, which means you take all the numbers and you reciprocate them. And that does all sorts of crazy things to graphs. Then you could also have the function inverse. Function inverse says you turn all the x's into y's and y's into x's. So on this graph we have 1, 1, 2, 4, and -1, 1, and -2, 4. So here are some points. 0, 0, 1, 1, 2, 4, -1, 1, and -2, 4. So the inverse of this graph is going to turn all of the x's to y's and y's to x's. So it would look like this. 0, 0 didn't change. 1, 1 also didn't change. 4, 2, 1, -1, and 4, -2. So now I'm going to graph the new set. 0, 0 didn't move. Here and here. Here and here. So that is my new graph. Which numbers didn't change? The ones where the x's and y's were already the same value. 0, 0 flipped and became 0, 0. Same with 1, 1. And you'll notice everything on the 45-degree diagonal stayed put. So everything, let me draw it differently, on that line didn't change. everything off the line flipped across the line. This point moved to here. This point moved to here. This point moved to here. Okay? Is the reflection, is the inverse a function? No, because it fails the vertical line test. So could I have known before I drew it that the original function did not have an inverse? We used the horizontal line test. So if I go back just to the blue graph and draw a horizontal line, it's still a function because every x only has one y, but the horizontal line test tells me there are two y's, or sorry, there's one y that goes to two x's. So if we look at our function bubbles, that's not a function, so we throw it out. Does this one have an inverse? No, because when I switch the x's and y's, we have one x going to two y's. So this one is not invertible because it fails the horizontal line test. If a function passes the horizontal line test, like this one, it's called 1, 2, 1, sometimes written 1-1. The only functions that have inverses are one-to-one functions. So being a function, every x has one y. Being one-to-one, every y has one x. And if you fit in both categories, then you're called a one-to-one function, which means you have an inverse. Okay, hopefully that was all review. So we're going to look at the graphs of logarithms and their inverses. So look at the first page of your worksheet. We're going to graph y equals log base 4 of x. But I don't have a log base 4. So I need to use the change of base formula. How would you convert that using change of base? This always trips people up for some reason. Let me make it easier on you. If it was log base 4 of 6, how would you type that in your calculator? ln 6 over ln 4. So, if I wanted to graph log base 4 of x, go into y equals, and I would graph ln x divide ln 4. And most of these graphs are really close to the x-axis and the y-axis. So we're going to change our windows from -6 to 6. So change your windows, -6, 6 on both the x max and min and the y max and min. And they'll be a little bit easier to see. So I graph ln x over ln 4. And I have drawn that 45-degree line. We'll get to that in a minute. So ignore that diagonal line. So this graph starts along the y-axis and goes like this. Does that graph represent a function? Yes, it does. Okay. What is the domain of that function? Do we include 0? So from 0, domain is 0 to infinity. 0 counts or doesn't count? Why does it not count? It never reaches 0 because 0 is an asymptote. Good. Okay. What's the range? From negative infinity to infinity, so all real numbers, or negative infinity to infinity. Either way. So I'll just write all real numbers. Okay, well, we learned earlier there are only two ways, so far, to restrict a domain. What can you do inside an equation that throws out x values? If you look at the graph, half of the x's are gone. There is no graph over here. What did we used to do to restrict domains? There were two problems we had. Do you remember those? Divide by 0. That creates infinity, which is not a real number. So dividing by 0 either created holes or asymptotes. There was something else we did on the last test. How else can you ruin a real number? What's that? Not fractions. Well, divide by 0 would be one. Square root a negative number. Well, are we doing either of those in this case? Because we've thrown out, well, more than half really, because we threw out 0 and everything to the left. So let's look at log base 4 of x and figure out what's going on. So log base 4 of x equals a whole bunch of unknown y values. Well, actually, I want to use y. That might make more sense. So log base 4 of x equals y. Okay. Well, let's convert this to exponent because it makes a little bit more sense like that. So in exponential form, this would be 4 to the y equals x. And the claim is, no matter what y values I use, this x is going to be restricted from 0 to infinity. Essentially, there's no way to get a 0, and there's no way to get a negative number. Why is that? Why does it work? Does it? Okay, so 1 is sort of a breaking point for the y's. So we're going to test everything against 1. Yes. Okay, so we kind of have these, I'm hearing when y equals 0 and when y equals 1, and those are the two breaking points. So let's just explore both sets. So 4 to the first. No surprise there. 4 squared. Oops, not 42. 4 squared, 16. I don't need to do this. What's going to happen when I keep going up? So I'm going to break the number line into 3 pieces. 0, 1, and so on. So at 1, the x value is 4. What happens as I go up from 1? Then the x value is going to get bigger and bigger. Okay? So no matter what I do over here, I'm going to get a positive number. Okay? So now let's test everything between 0 and 1. What is 4 to the 0? 4 to the 0 is 1. What about 4 raised to the 0.5? That's the square root, right? So 4 raised to the 0.1, that would be 10th root. So 4 to the 0 is 1, and all of these numbers are going to yield what sort of numbers? Positive numbers between 4 and 1. Okay? So every number between 4 is 1 represented here, and if I go to the right, I reach all the way to infinity. Okay? Let's test negative numbers. 4 raised to the negative 1 is 0.25. 4 raised to the negative 2. Anybody know that decimal offhand? Close. It's a 16th. It's 1 over 4 squared. So 4 to the negative 3, that's going to be 1 over 64. Okay? Well, what if I do something really big? 4 to the negative, I don't know, 12. What is that number? It's a really small decimal, 0.00000005. Okay? So what's the lowest possible value I'm going to get by putting really large negative numbers in there? Lots of zeros. So I'm going to get close to 0. Am I ever going to reach it? So going back to the original question right here, if y is bigger than 1, I get a positive number, a big positive number. If y is between 0 and 1, I get a number between 1 and 4. If I plug in a negative number, I get a number between 0 and 1. There is no way to use an exponent to create a negative number. And that's what's really going on. Regardless of the y value I choose, the x values will always be positive. So that's another way to restrict the domain, is to put a variable in the exponent. So you can divide by 0, you can square root negative numbers, and you can use logarithms. Those are the 3 ways to restrict domains. Okay? And you can also kind of do some things with trig. Well, not really. Never mind. Scratch that. Okay. So on to number 1. We want to graph y equals 15 to the x. So graph 15 to the x. And it's also going to be helpful if you graph x. Y equals x is the equation of that 45-degree inverse line. So I graph this, and it looks like that. And I'm going to draw the dotted inverse. That looks a lot like the logarithm equation, only inverted. So when I graphed log base 4 of x, I got something that looked like this. Well, those look like inverses, right? Exponential graphs and logarithm graphs are, in fact, inverses. So let me show you how to calculate the inverse, and then we'll graph it. So if I take y equals 15 to the x, I want to take all the x values and switch them with all the y values. How do I do that? Well, I could use a table. I could write, I don't know, 20 of them down, and then switch them and graph it. That's annoying. We don't want to do that. There's a really easy way to do it. Switch the variables, and all the points will come along for the ride. So the inverse, this is f of x, right here. F inverse of x is represented by x equals 15 to the y. And that takes all the points and switches them for us. Okay, but now I can't graph it in this form. What do I need in order to graph a function? The y's got to be by itself. So we use logs to convert this to set the y equal to itself. So you can ln both sides, drop the y. Ln x over ln 15 is the inverse. So I go into y equals and I graph in y2 ln of x divided by the ln of 15. And those two functions should be perfectly mirrored across that y equals x line. So you kind of have 2 parts to this. You have to graph the function and graph its inverse. But in order to graph the inverse, you have to invert the equation to do so. Okay? So let's look at number 3. No, let's do number 4. It's kind of more fun. So I'm going to graph this ln of 0.67 divided by the ln of x. Okay, see what that looks like. Did I not get rid of the other one? Oh, I did it backwards. Yeah, that definitely didn't look right. ln of x divided by the ln of 0.67. There we go. That looks better. So this looks like that. Okay? So the inverting step is easy. Switch x and y. X equals log base 0.67 of y. Now I need to solve for y. How do you get the y by itself? Convert back to exponent. So 0.67 to the x equals y. So I go in and graph 0.67 raised to the x. Are those inverses? Yes, they are. So the other one looks like this. And they are perfect inverses. Okay, pretty simple worksheet. You should be able to get it finished in class. Good luck to you. It's due tomorrow.